All right. So concerning about the test number 2, I think the students who follow the class, every Tuesday and Thursday, did pretty well in the test. And I'm still working on that, and we'll try to post the results within 1 week. Okay, so probably next Tuesday or so, you will have the grade for test number 2, right? Okay, so now let's learn the next topic that I introduced last time. Is about dynamic programming. Okay, so uh, last time I used one example about, say, Fibonacci number, right? And using the Fibonacci number, you know that if we choose divide and conquer, then the biggest problem with divide and conquer approach is that some of the calculation will have to be repeated, uh, many times. In fact, we don't have to repeat the calculation, but because of the divide and conquer, we have to recalculate again and again. That is not necessary. So that's why we want to learn the next programming technique we call dynamic programming. Okay? So dynamic programming is used for solving many real-world applications. Like last time I showed you about, say, if we have two assembly lines for vehicles, how can we find the best way to send a new chassis to whether or not, say, line 1 to line 2 or continue on line 1, etc. Okay? So we will try to solve such real-world application problems using this technique. Okay? So here we have a problem that we have to find an optimal solution, meaning that we will have a set of choices, and we have to write a program so that we can pick the optimal ones. So of course, there may be more than one optimal solutions. At least we can find one for that purpose. Okay, so that is the overview of dynamic programming. So let's move a little bit through this, say, assembly line scheduling a little bit. I will come back to this point after we learn some fundamental techniques first, right? So we have two assembly lines, right? And the assembly line may have different, say, working conditions. And sometimes when we have a new chassis for a car enter, it may not be the best to go through one assembly line because some of the stations here may be working too much, and hence the waiting line may be bigger at here and there, right? So in that situation, it may be better to go through station 1 and then go to station 2 in line 2 and then continue and then go back, etc. Right? So that said, this one is a real world problem, and it will help the producers like Tesla to increase the way or the number of cars they can produce. Okay? Tesla is one example in that they use programming, artificial intelligence programming a lot. So that's why it helped them to speed up the process, and as the result, they produce a lot of cars, right? Okay, so it's one real-world applications, but we will start with a simple thing that last time I also introduced before, that is about matrix chain multiplication. We have a sequence of matrices, and the matrices are compatible. Right? So we have a list of matrices. With each of the matrices, we have the number of rows and the number of columns. Right? So we want to find out what is the results after we multiply all of them together. And as we know, matrix multiplication has the associative property. It means that it doesn't matter which one you multiply first. You can multiply these two first, right? And then multiply with the rest next, etc. The final results are always the same. However, the way we multiply them will take different number of times, meaning that if we choose the wrong order to multiply the matrices, then the program will take much longer time, sometimes 1,000 times slower if we pick the wrong order. Okay, and matrix multiplication is needed for solving approximation of differential equations, and that has many applications in engineering. So that's why they want to find how to find the best way to multiply the matrices. By the way, you have two matrices, A and B, right? Each of them have a row and a column, right? And in order to multiply them, A and B have to be compatible, meaning the number of column of A has to be the same as the number of row of B, right? So that's why we can multiply them, right? Okay, so if we have a sequence of matrices like this, then they have to be compatible. It means that the column of the first and the row of the second, the column of the second and the row of the third must be the same. Otherwise, we cannot multiply them, right? Why? Because when we have two matrices, say A and B, right? Multiply them, we'll have a result that has the same number of rows like A and the same number of columns like B, right? And then every element in this resulting matrix will be the accumulation of multiplying one element here with one element here and accumulate them, right? I will go this way and J will go this way and we accumulate them, right? So that's it. We accumulate the result here to Cij, and then finally, after we finish the loop, yeah. So here, right, for every k, then the results of Cij will be put here as the result, right? And we have to do it for every row and every column, right? So that's it. Multiplying two matrices is easy, right? We just have every element on the row I and every element on the row J, multiply them, right? It's easy, and it's just a reminder if you forgot about that. Okay, so we have a list of matrices, and as I said before, you can choose any one of them to multiply first and then do the next, right? So like here, we can multiply these two together first, and then these two together next, right? And then after that, you can multiply the result here with the next one, etc. Right? So many ways to multiply. So for example, here, if we have three matrices, you can multiply A1 and A2 first. After that, multiply with A3, or multiply A2 and A3 first, and after that, multiply with A1, right? The results are the same, but the number of steps or the number of small multiplication of elements will be quite different, right? So last time I showed you some examples. For example, if we have A1, A2, and A3 like this, right? Here are the number of rows and the number of columns, right? Now, if we multiply A1 and A2 first, and after that multiply with A3, how many steps or how many small multiplications of elements do we need? So first we multiply A1 with A2, right? A1 has 10 by 100 and A2 has 100 by 5. So it means that multiplying these two matrices will cause, right, 10 by 100 by 5, which is 5,000, right? And the resulting will have 10 row and 5 column, right? So when we multiply A1 and A2, we have a result is a matrix, and that matrix we have 10 row and 5 column, right? So that set is 10 by 5. Now multiplying with A3, and A3 has 550. So it will have 10 by 5 by 50, right? Yeah, that is 2,500. So we add these two together. So the number of multiplication of elements will be 7,500, right? Just add this one and this one. Now, if we multiply the matrices in a different way, for example, we multiply A2 and A3 first, the number of element multiplication will be A2 100 by 5 and then 5 by 50. So multiplying these two matrices will cost 100 by 5 by 50, which is 25,000, right? And the resulting will have 100 column and 100 rows and 50 columns, right? So here is the size of the matrix after we multiply A2 and A3. Now we multiply A1 with this matrix. We have what? 10 by 100, right? And by 50, we have 50,000. All right. So add them up, we have 75,000. So you can see here, if we multiply A1 and A2 first, it took 7,500, right? If we multiply A2 and A3 first, it's 75,000. Okay, so that is a big difference, right? So we even have some examples in that the cost may be 1,000 times different. Yeah. So for example, here we have another set of matrices. We have 4 matrices, A, B, C, and D, right? So similarly, you can check by yourself at home that if you multiply BC first, right? After that, you multiply with D, and after that, you multiply with A. The total number of steps, meaning element multiplication or multiplication of integers. Suppose that the elements in the matrices are integers, right? And if we multiply this way, then the total number of steps is 1,400. And if we multiply this way, AB first, and then CD, and then multiply there. Here we have 41,000, right? So it's about, say, 40 times, right? Or 30 something times more. So that is why we want to find out the best way to multiply the matrices. So we have 4 matrices, A, B, C, and D. What would be the best way to multiply them? Whether or not AB first or BC first. right? So how can we do that? How can we find the best ways? So number one, this problem is what we call the optimal problem, right? We have to find the best way, or in other words, the optimal way to multiply the matrices, not any way, okay? So one thing we can do is that we can do exhaustive search, right? So we have 4 matrices, just try on possibility, right? But try on possibility is not a way we should follow, because computer scientists like us cannot afford that kind of naive solution. Right? You have 4 matrices, try on possible way to multiply them. Okay, so how many possible ways we can have if we have n matrices? How many possible ways we can have? Anyone? Caleb? If you have 4 matrices, how many ways you can try? If you have n elements, okay, how many ways we can shuffle the elements? John? Yeah, I mean, in general, it's about n factorial time, right? Okay, so that is what we have, but we cannot afford that, because if we have about, say, 20 matrices, in the real world, if they want to solve a differential equation, they may need to multiply 100 of them. And then if 100 okay, so we need n factorial, and if it's 100 factorial, then it would be way too much, right? The program cannot finish if we go through all possibilities like that. Okay, so exhaustive search is not a good way. So how about divide and conquer? Divide and conquer means that if we have a big problem, we can divide and conquer the small parts, right? So in this situation, we can use divide and conquer as well. But let's see how much, or I mean, what would be the complexity if we try to use divide and conquer. So first, we will try to design an algorithm in that we use divide and conquer. So how can we do that? Remember that if we have a list of matrices, right, we can divide it at any point. For example, we divide here, right? And we will see if we divide, what would be the optimal cost for the left portion and the right portion. Okay. So in other words, we will try all possible way Okay, cut it here, cut it here, cut it here, cut it here, cut it right before the last, right? So at any cutting point, that is, we cut it at the K, right? The K position. If we cut at the K position, then the K can be before the I, right? Or before the J minus 1. We want to have an arbitrary list, not only from 1 to n, right? Because here we divide, then we have a smaller list. So that said, we want to find out what would be the optimal cost if we multiply a sequence of AI to a J matrices. So at the beginning, I will be 1 and J will be m, for example, right? And then after we break it here, we will see what is the cost for the left, the cost for the right, the optimal cost for the left, the optimal cost for the right. Yeah. So that said, so the optimal cost for multiplying a sequence of matrices from I to J, right? From I to J will be the minimum cost for all possible way to cut the big sequence. So if we cut it at K, where K is between I and J minus 1, right? So we cut it here, or we cut it here before the J, then we simply find out what is the minimum cost for doing that. Okay? The minimum cost, if we cut it at K, will be the minimum cost for the subsequence from I to K, right? From I to K, and from K plus 1 to J. So if we cut it here, then what would be the optimal cost from I to K, and then the optimal cost from K plus 1 to J, plus the cost for multiplying this result with this result. Okay? So remember that after we found the optimal cost for multiplying this sequence, then the result will be a matrix that has the sign of what? Di minus 1 and dk. Okay? Assume that here matrix I will have di minus 1 times di. Okay? Row, column, right? So the result here will have d minus I row and dk column. And the next one will have what? dk row and dj column. So if we multiply this result and this result, then we need to add that cost into the optimal results. That is di minus 1 times dk times dj. So that is the extra cost when we multiply the two sub-results together. Okay? All right, so that said, if we design or if we calculate the minimum cost or the optimal cost like that, then we can see that it looks like a recurrence for us, right? Or in other words, it looks like we have a divide and conquer algorithm already. Okay? So here, if we have the optimal solution is calculated like this, okay, we can design an algorithm as follows. We are given a set of matrices or a sequence, right? And we want to find out what is the minimum cost for the sequence from I to J, right? Okay. Then we simply have the base case. If I equal J, meaning the sequence has one matrix, then the cost would be 0, right? Because one matrix, we don't have to multiply anything. So that said, we have it here. Now, we will try to have the K again from I to J minus 1, right? And then we calculate the cost from I to K by invoking the function minimum cost MC again, right? Recursively. So we would invoke the function again from I to K, from K plus 1 to J, and multiply the cost for having the two matrices here together, right? Then that is Pi minus 1 times Pk times Pj, okay? Is the value we have from the previous slide we have here, right? Each of the matrix we have row and column, right? Row and column, row and column. So that's why we have here the cost, right? The row, the column, and then the column of the last matrix. So if the value is smaller than m, meaning we try to find out what is the minimum value, right? So initially we set it into infinity or max in, or the max value if we use Java, okay? And then if it's smaller than m, then we accumulate that, right? So after we go through all possible way to cut, then we return m, right? So this one is a recursive algorithm, right? Recursive solution, we have it here. Of course, we need to invoke MC from 1 to m, right? So we invoke MC. Then that is the result we need to see, right? But here, because we have the divine concur, so we need to write a more general program that deal with I and J for I and J between 1 and n, right? So the solution, the recursive solution is here, but this algorithm, as you may expect, we have to calculate some of the values again and again in a similar manner like we have for the Fibonacci number. Okay, so we expect that this algorithm will not be a good algorithm. So in order to do that, we need to analyze the complexity of this algorithm. Okay, so what would be the complexity? Again, you learn about how to analyze the complexity, right? So if we call the number of steps when we have n matrices in the sequence, and let me choose a different color. Just okay. Okay, so if we have Tn is the number of steps when we have n matrices in the sequence, then what do we have? So from here, you can see that the first step here, take a constant number, right? So the base case, take a constant number. And then after that, we have to go through every possible way to partition, right? So that said, it will be the sum of finding the optimal solution for the first k element, right? That is tk, right? When k from 1 to n minus 1. And then the rest will have n minus k elements. So Tn will be Okay, 1 plus the sum here, and plus 1 here comes from this extra cost. Okay, let's choose a different column. Okay, here we have 3 multiplications of the elements, meaning it's bigger one, right? So Tn is here, right? And we know that when k from 1, we have T1, T2, T3, T4, T5. And at the same time, the rest will have n minus 1, n minus 2 to 1, right? So it's similar to what? I think we already learned how to analyze the complexity very similar to this before. Where did we have it? Yeah, when we calculate the average cost of the quicksort. Very good, right? So we will use that result for the same purpose here. So here we have the sum of tk and t of n minus k, right? For k from 1 to n minus 1. And actually these two sums will be the same, right? One come from 1 down to n minus 1, and the other one will go from n minus 1 down to 1. So in other words, this sum will be 2 times tk, right? Okay, so because these two terms, when we sum them up, we would have the same summation. So that's why we have 1 plus 2 times tk plus 1 for k from 1 to n minus 1, right? Okay, now how can I solve this recurrence Tn? What did we do when we analyze the quicksort, average case of quicksort? We have Tn is 1 plus the sum from 1 to n minus 1 of 2 times tk. Okay, we can bring 2 out, right? And then 1 here will be big O(n), right? Okay, so we can simply take the sum of tk, right? So how can I find what is Tn? I need to know the complexity of this function, right? After analyzing, I have Tn is here. So what is Tn? What is the solution for Tn? Brian Jacobs. So I have Tn here. How can I solve the recurrence for Tn? Okay, so who can answer that? Jared Martin? You're quiet today, huh? So how can I solve this recurrence? N log n, not possible. Okay, not possible. Okay, so remember that when we have Tn as the sum, what we will do is that we have to remove the sum, right? How can we remove that? We would need to write down what is Tn minus 1. Have it here. what is Tn minus 1 here? What is Tn minus 1? Just replace n by n minus 1 on the right hand side, right? On the right hand side, you have what? Sum from 1 to n minus 2 of 2 tk, right? And then you subtract the left and subtract the right, then we will be able to get rid of the sum for the right hand side. Okay, so it's the technique we use when we analyze the complexity for quicksort, right? More precisely, the average case. Okay, so that said, on the left hand side, if we replace n by n minus 1, on the right hand side, we have this. Right? Now, we subtract the left and the right. So on the left, we have Tn minus 1. On the right, we have the sum of Tn. Tn will be the sum from 1 to n minus 1, right? And subtracting this sum, you would have, okay, 1 will be cancelled, and here we have 2 of Tn minus 1 plus 1, right? Okay, so that is what we have after we subtract. So now we can bring Tn minus 1 to the right-hand side. So we have Tn is 3, okay? Bring this one to the right-hand side. Then you have 3 Tn minus 1 plus 1. Okay? So what is Tn? Tn is 3 times Tn minus 1, right? 3 square times Tn minus 2, etc. So the result will be 3 power to the n. Okay, so it's an exponential algorithm. So that's why the algorithm we have here is pretty simple, right? Use divide and conquer. But after we analyze the complexity, we found out that this algorithm takes 3 power to the n, which is exponential. And hence, actually it's very similar. The complexity is as bad as the exhaustive search. Okay, remember that exhaustive search takes about n factorial, right? N factorial is also exponential. Okay, so in this case, divide and conquer has the same complexity like we have for the exhaustive search. Check all possibilities, right? So in that sense, divide and conquer is not a good algorithm here for solving this particular problem, right? So that's why in say CS1, CS2, I mean CMPS 165 and 280, you learn some simple programming techniques, right? And in CMPS 390 data structure, you learn a little bit more about data structures needed for designing a good algorithm, right? But divide and conquer and the exhaustive search still not enough for us for solving some real-world applications. Okay, a real-world application cannot accept a program or an algorithm that is exponential like this. Okay, for very simple reason, it will take months, if not years, for solving complicated differential equation, right? So like here, if we have 100 matrices or 200 matrices to multiply them together, finding the best way if we use the algorithm here, it will take a month or two, right? So that's why we don't want to have the divide and conquer approach like this. Okay. Now, how can we solve the problem? Remember that the problem with this is that when we invoke the function MC again, some of the calculation will be repeated unnecessarily, okay, again and again. So that is why the algorithm is so slow. Okay, so how can we solve this problem? We will try to do a little bit different. Okay, so remember that for the Fibonacci number, we can design and say recursive algorithm that like say exponential number of steps, right? But we can also remember the previous calculation and then simply use the previous result instead of recalculate them. Okay? So similarly, here we will try to remember it's very similar. Yeah, we try to remember. Say, if we already know the optimal way for multiplying matrices from I to K, and then from K plus 1 to J, can we store them? And then when we need them again, we simply use them, right? So that is the idea. And the idea will give us a much better solution. So remember that the previous divide and conquer algorithm has this complexity, right? Now, we will try to have it with an quick algorithm. Okay, how can we do that? Okay, so here is what we will do, right? The algorithm is here, but let me start with one simple example to show you how the algorithm works first. Okay, so here is what we have. It's a little bit. Yes, so the color, hopefully you can still see it, okay? I will change it on my slides, but hopefully you can still see it. See, here is what I have. Okay, so I will use two tables, okay? And each of the table will have 4 rows and 4 columns because here I have 4 matrices. I want to find out what is the best way to multiply these 4 matrices together, right? Whether or not multiply the first 2 or whether or not multiply the last 2 first, okay? So I will try to say record the previous calculation. So I will start with 2 tables and then I will number them here. Okay. Maybe just write. Okay. 1, 2, 3, 4. 1, 2. Oops. Okay. Maybe just use the. Okay. Here I have 1. Here I have 2. And 3. And 4. Okay, and then same thing I have here. 1, 2, 3, 4. Okay. So now what I will do is that I will try to find out what would be the cost for multiplying 2 matrices, 3 matrices, and then finally 4 matrices together, right? So I will try to go diagonal by diagonal, okay? So now what does it mean? The first table will tell me the cost. Okay, so the first table will tell me the cost. Yeah. I call it the cost table. Okay, and then here is the position. Okay, I will record the place where I break the sequence. Okay, here is the cost, and here is the position. Yeah. So now, first, try to have the first diagonal. Now, the first diagonal will tell me, okay, what is the minimum cost for multiplying the sequence from 1 to 1, and then 2 to 2. Okay, so what is the cost? What is the minimum cost if I multiply the sequence of matrices starting from 1 and ending in 1? Meaning I have only 1 matrix, right? So again, here I will number that 1, 2, 3, and 4, right? So if multiplying a sequence from matrix 1 to matrix 1, the cost will be 0, right? Because you have 1 matrix, you don't have to multiply anything, right? So that said, the cost here will be 0. Same thing, 2 to 2, the cost will also be 0. Okay, 3 to 3, 0, and then 4 to 4, 0. So basically, the main diagonal, we have the cost of 0, right? Okay. So how about the position? If I have the sequence from 1 to 1, so again, here I will have 1, 2, 3, 4. Okay, let me copy them, and then we will try to have it. Okay, so I can copy this one. Okay, so we will try to write it. Okay, so we will write it down again. Okay. 1, 2, 3, 4. Okay, and then 1, 2, 3, 4. Okay. So the position, if we have a sequence from 1 to 1, what would be the best way to break it? We don't have anything to break, right? So that's it. This diagonal, we have no value. Okay. Now, the next thing I will do is that I will follow this diagonal. What does it mean? It means that I want to know what is the minimum cost if I multiply the sequence from 1 to 2. Okay, 1 to 2, 1 to 2. Okay, how can we multiply? What would be the minimum cost for multiplying from 1 to 2? There's only one way, right? There's only one way. That is multiply them directly. Okay, and what is the cost? So this cell on this diagonal will tell us what is the cost for multiplying the subsequent from 1 to 2. Okay, so what is the value we have for this cell? Multiplying from 1 to 2, you have 3 by 2 by 4, right? 3 by 2 by 4, which is 24, right? Okay, so we write it here, 24. It's the only way to multiply them when we have two matrices, right? Similarly here, what we have for 2 to 3. Can someone tell me? So this value, what do we have? 2 to 3. The sequence from 2 to 3. Two by 4 by 3, right? 2 by 4 by 3, which is 24 also, right? So 2, 3. We have 2 by 4 by 3. Also 24. Now 3 to 4. What do we have? 3 to 4. We have 4 by 3 by 5. Right? Okay, so we don't need to write it down here. We can write immediately the result to this cell. What do we have? 60. Very good. Okay. All right. So that is the sequence of two matrices. So remember that first we try to record or remember the cost for all sequences with one matrix and then two matrices, and now we go to three matrices. Okay. Now we want to know what is the cost for multiplying from 1 to 3. Remember that 1 is here and 3 is here. Okay? So what would be the minimum cost for multiplying these three matrices? Three matrices here, we have two different ways to break the sequence. One is here, right? Okay? So that said, if we break it here, what is the cost? If we break it here, on the left, we have from 1 to 1, right? It's 0 plus, oops, 1 to 1 is 0 plus from 2 to 3, but we already know the cost for multiplying from 2 to 3. We just have it here, 2 to 3 is 24, right? Plus with the cost of multiplying them together, right? So what is the cost for multiplying the left subsequent and the right subsequence? That is 3 by 2 by 3, right? Okay, so 3 by 2 by 3. Okay, so the cost for the left, the cost for the right, and then the cost for multiplying them. Okay, 3 by 2 is 6. 6 by 3 is 18, right? Oh, where did I have? Okay, so we have 6 by 3 is 18. So it's one way, right? The other way is what? The other way is by breaking it here. So I will choose a different color. So okay, if we break it here, the cost for the left will be 1 to 2. We already have it. 1 to 2 is 24, right? Okay. $24 plus, okay, 3 to 3 is 0, we know, okay, plus what? The cost for multiplying them together, okay, is 3 by 4 by 3, okay, 3 by 4 by 3. Oops, it should be right now. Here. Three by 4 by 3. Okay, so which one is bigger? 24. This one is bigger, right? So the smaller one will be this. 24 plus 18. So it will be the smaller one. Okay, so that's it. From 1 to 3, the cost will be the first way when we break it here, right? So that set is 24 plus 18 will be, okay, 4 plus s is 12, okay? So we have here 2 by 1, 2 remember 1, so we have 42, right? So this one, we would have 42, right? And let me use the color here. Similarly here, we don't have the value on this diagonal, okay, because multiplying two matrices, we don't break it anyway. But from 1 to 3, we have two different ways. And the best way is by breaking it here at this place. Okay, so we record that position. We have two different ways, but the best way will come from the partition at the position 1, right? So it will be the position 1. So we record it here, right? Okay, so that is what we have done with 1 to 3. Now the next one will be 2 to 4. Okay, remember that we are talking about matrices that has 3 elements, or the 3 matrices sequence, right? So let me remove this so we can go back to work out. Okay, so now we have 2 to 4, right? 2. Let me use a different color. Okay, now we have 2 to 4. Again, we have 2 different ways, right? One is breaking it here at 2, right? So if we break it there, then what would be the cost, the minimum cost for doing so? Okay. Here, the cost for the left is 2 to 2. We know that is 0, right? The cost from 3 to 4, we already have it here. 3 to 4 is 60, right? And the cost for multiplying this one and the result here together, it will be 2 times 4 times 5. Okay? 2 times 4 times 5. I will leave it here first because I want to see what number I have for the second option. Okay? The bigger one, we don't need to multiply. So that's why we simply want to see what we have. Okay, so the next way to multiply them is here, right? Use a different color. Okay, so we break it 3, then the left will be from 2 to 3. 2 to 3, we have 24, right? So 2 to 3, we have 24. And then plus with the right subsequence 4 to 4, we know that is 0. Okay, so it should be 0 here. Okay. Okay. 24 plus 0 and the cost for multiplying the result together. So what are they? The cost for multiplying this result and this will be 2 by 3 by 5, right? 2 by 3 by 5. Oops, where is it? Two by 3 by 5. Okay, it's 30, right? 30 here, we have 54, right? Okay, so this one will be the smaller one. So this one is 60, is already bigger than everything we have here, right? So we have here 2 to 3 is 24, right? And then the right is 0, and the cost for multiplying this is 2 by 3 by 5. Okay, it's 30. 30 plus 24 is 54. So we write it down here. 54 is the smallest value, right? Or the smallest cost. So now I can remove this one. Okay, so 54 is where we got it right here at 3. And hence, I will write it down here. The position for having the best multiplication way for 2 to 4 is at 3. Okay, so that's it. We got it at the position 3. Okay? All right. So now we will try to fill out the last cell or the last diagonal, right? That is from 1 to 4. Okay? Now, 1 to 4, let's see what we have. So from 1 to 4, for this sequence, we have 3 different ways to break the sequence, right? The first way is here after the first matrix, right? So what would be the cause if we break the sequence at this place? So we would have the values like this. Okay, so if we break it here, the left has the minimum cost of 0, right? Because the sequence from 1 to 1 has 0, and the second subsequence from 2 to 4, 2 to 4 is 54, right? 54, and the cost for multiplying the sub results would be 3 by 2 by 5, okay? 3 by 2 by 5. Okay, so that is 30, right? Okay, so now I will not multiply them, but wait for the other calculation before I multiply the values actually, okay? So now that is the first way. The second way is here. I will choose a different color. Okay. Break it here, right? Okay. So when I break it here, the left, the right, and then the cost for multiplying the sub-results together, what are they? So I will choose the same color here. What will be the result of the values I have if I break it here? The left is from 1 to 2 is 24, right? So 24 plus, okay, 1 to 2 is 24, right? Plus 3 to 4, 3 to 4 is 60. Plus, with the cost, okay, for multiplying them together. But it looks like it's already bigger than what we have here, right? Okay, so I will write it down, but we don't need to do the calculation because it's already, the total is already bigger than what we have when we have the first way to curve it, right? But let's have it. Here we have 3 by 4 by 5, okay? 3 by 4 by 5. Okay, we don't have to do the calculation. Now, the last way would be, let me use a different color. Okay. The last way will be here, put it at 3, right? So what will we have? if we cut it here, the left is from 1 to 3, right? 1 to 3, I have 42. So that's it. Here I have 40. Okay. 1 to 3, 42. Plus 4 to 4, we know that is 0. Plus the cost for multiplying the left and the right, it will be 3 by 3 by 5. Okay, 3 by 3 by 5. So what would be the smallest value? This one is 9 by 5 is 45. And this one will be 87, right? 87. And this one will have what? And the first one, we have 84. Okay. So the smaller one is by breaking at this position, right? So that's said. Let me use the color here. Okay. So here we have 84. And the way we break it is that one. Okay. So we are done with recording all of the intermediate results. And then when we break it, we simply use the result we had stored before, right? So here is the final result. So what does it tell me from the results here? What it tells me from the cost table is that the minimum number of multiplication is 84. Okay. Now, how can I obtain the way to multiply the matrices so I can have the optimal result? Finding that, I will look at this matrix. Okay. First, I break it at 1, meaning break it here. And now I have from 2 to 4. Okay. 2 to 4, the best way is to break it at 3, meaning I will have it here. Okay. And all it tells me is that first multiply 2 and 3, after that multiply with 4, and then finally multiply with 1. Then I have the minimum value, like that. Okay? So time is almost over, so I will give you one hands-on exercise. You can practice, and on Tuesday, we will continue with this by analyzing the complexity of the algorithm to see whether or not it's better. Actually, it's much better than the divide concur. Okay, so here is what I have for you. Here I have the sequence of 4 matrices again. Okay, write it down and then try to do it by yourself at home. Okay. Tell me what would be the best way to multiply these matrices together. And what is the best way? What is a best way? You may have more than one best ways. Yeah. And what would be the minimum cost by doing exactly what I just go through one by one steps with you before. All right. So any questions so far? Okay. If no question, then we will stop here.